Good afternoon, everyone, and welcome to the sixth CPD webinar in this series that we're running on sustainable drainage systems. And today's event is just going to cover the auditing aspects. We've been through a systematic approach of designing said systems. And what we'll do now is take a look at how we go about the auditing process at the end of that design. On my own today, so running solo, apologies if I can't answer any questions live because I'm just concentrating on the actual presentation and the demonstration, but I will promise to answer all of your queries that you flag up during the course of the event, subsequently following on from the event. So what we'll do today is take a look at just a quick refresher on the SuDS philosophy that we're trying to engender and identify those key standards that are currently changing quite a bit as we speak and coming through, and identifying the targets that we need to meet with our SuDS designs. And this involves a systematic approach on the auditing process, and we've run through a systematic approach on the design process, and that's what I'll follow through today. A reminder on the philosophy that we're trying to implement pretty well globally is that we're looking at source to capture that rainfall, to really embed sustainable drainage systems into surface water management and also the water cycle. So at source, where the rain is falling and the runoff's being generated, we ideally would like to put in some kind of rainwater harvesting, put in green roofs maybe, permeable paving. In terms of the UK, we have to gain planning permission now to extend our drives in the front of the properties to ensure that it is permeable paving, maybe implement water gardens, etc. So we're utilizing that free resource, the water that's landing on our heads right at source. But there's more to it than that. What we also need to do is look at those extreme events. We're having to help communities now that are at risk to flood. So we're looking at the provision of surface water management systems. And to provide this, we really do have, at the very concept, have to consider the connectivity. Where is the overland flow likely to run? And we covered this in earlier webinars. But I'm looking at the connectivity, and not just the connectivity of the quantity of the water, but we're also trying to engender these multiple benefits that are available to us if we identify those blue/green corridors at an early stage of the process. If we can utilize those areas as public open space, then we can maximize the benefits and we can improve the ecosystems and we can improve the biodiversity aspects as well. So I'm thinking of connectivity within the urban environment, but then connecting that urban environment to the rural environment. So we've got seamless integration, if you like, between our sites. We're going to develop integrated models, and then that model, that site, will fit nicely into our integrated catchment approach that we're now working across Europe with, and indeed globally. So how do we go about this? Well, we look at things at source, as I mentioned, at the property level. We also look at things stepping up a scale to the site, and then we look at things regionally. So there are three scales, if you like, of zooming out and zooming back in on developing this systematic approach. Why are we doing this? Well, we're trying to protect communities. I've said here, protect the new development. I'm actually thinking of the poor folks that get flooded and affected by this. I cannot express in words the trauma that this provides, and the fact that we can actually mitigate around at design, at concept. There is no excuse in my mind now why we should not be better protecting communities with the impact of a catchment affecting the development and also the development affecting the existing catchment. It works both ways. And I'm thinking of long-term performance. And of course, we have a range of stakeholders involved, some with shorter-term objectives than others with longer-term objectives. I'd like to thank Rachel Dearden for the images that I'll use over the next couple of slides from the BGS, the British Geological Survey. And this is showing you the kind of things that we can do at source. Implementing maybe soakaways. We could put a green roof there maybe. A water butt, rainwater harvesting, all will help. And I really still cannot understand why we're paying to have potable water supplied that we're then spraying on the garden when we can capture it and utilize it ourselves. But there we go. This is where we're at. But this is identifying what we could potentially do literally at source. And if we had the ground conditions, and probably about only 25% of the projects that we deliver in the UK will be in this kind of ground where we could percolate into the superficial deposits below. Normally, we're working with either high groundwater tables or in clays, rocks, etc., etc. So 75% of the time, we're probably going to be in clay soils. I totally appreciate that. But if we do have the opportunity to infiltrate, then we should take it to recharge the aquifers, and we should take it in terms of reducing the volumes of storage that we need to provide under the ground, which will reduce the costs. So we need to balance that economic argument along with the environmental argument and fit that in with the needs of the community for the long term. When we look at the site control options, this is where we introduce things like swales or infiltration trenches or just filter drains alongside the highways, and they can interconnect. And at a regional level, we can then look at the larger items such as wetlands, retention ponds, larger infiltration basins, etc. So the two shots down here, let's thank Dave Schofield of Hydro Consultancy for this shot. This is an infiltration basin in the Midlands, constructed quite a few years ago. You have a trench taking the low flows, and then when the extreme rainfall events occur, like the 30-year, Dave's designed this infiltration basin to fill up to a certain level, to provide you with flood mitigation measures to ensure there's no flooding for the 30-year return period. We can gain benefits here. I mean, that's a nice looking situation. It's providing amenity. People in the business park can come out and picnic here for lunchtime. If the weather's better than it is today, and I'm not sure how you're doing, but it's not too great here in Newbury. But anyway, you can provide amenity. We can provide biodiversity and improve the ecosystem. Far better this than just a concrete pipe buried under the ground. On the right-hand side, this is a business park in Aztec West in Bristol, designed in the mid-70s, built in the late 70s, early 80s. And this pond here, there's actually two cascading ponds. This is the first one, and then there's a culvert underneath the highway here connecting to another pond. So they're cascaded together. These have been in service for about 35 years, and they are very well appreciated by the owners and also adding value to the rentals of these properties on the business park. Reminding those that were on the webinar last time, the Welsh Government have produced an excellent consultation document that closes on the 30th of April. And what they have done within this consultation document, it's an interim document, non-statutory standard for sustainable drainage systems throughout Wales on how to design, how to construct, operate and maintain surface water drainage systems. And they've taken all of those SuDS philosophies and introduced them into this one standard. It's about a 76, 80-page document, very comprehensive, and I'm impressed. It takes into account climate change. It takes into account that once people have moved into properties, we extend them. We extend the drives, we put on conservatories, patios, etc. So that urban creep will increase the runoff over time, probably about 10% within the first 5 years of a development being completed. An extra 10% of impermeable area will creep into that development. They look at the interception methodologies to ensure that I don't really like the word mimic the Greenfield runoff condition, but in essence, what we're trying to do is convey flows as they would have conveyed naturally pre-development in that Greenfield condition. They're also targeting the need to limit the peak discharge rates, the runoff rates from the site, and ensure there's no flooding for the 30-year. Understand that there will be flooding beyond that event, and identify the overland flood routes for the 100-year plus the climate change, and ensure that the community are protected. So we're introducing surface water management right at the design phase, so we can go beyond the design, create the flooding, and identify the overland flood routes, and make sure that we don't internally flood any properties, breach a threshold. They're suggesting that we use surface storage mechanisms, and when they say surface storage, they're incorporating permeable pavements into that discussion, and they would like everyone to demonstrate what they have produced in a runoff model, an integrated runoff model. Importantly, they're introducing the need to look at the runoff volume that's generated for a specific event. This is quite common. This is the volumetric runoff calculation that we've been doing for many years now to satisfy documents like the Code for Sustainable Homes, the Interim Code for Sustainable Drainage Systems, etc., the Code of Practice. So the key targets that we're looking for hydraulically, and that was the hydraulic section of the consultation document that I've just summarized, is looking at the peak discharge volume, the peak discharge rates. We can also look at water quality, and we can look at the minimal discharge rate. And this is for the first 5 millimeters of rainfall, so known popularly as the first flush. The more highly polluted runoff is the first flush. So we can take a look at that, ensure there's no flooding for the 30-year return period, and incorporate climate change, looking beyond where we are and identifying those overland surface water management paths. A quick word on the peak discharge rates. If we can reduce the volume or match the volume post-development to that was generated Greenfield or pre-development, then we will be allowed to discharge the 1-year, 30-year and 100-year peak discharge rates post-development. If the volume that we generate post-development is greater than the Greenfield volume, then we'll be limited to one discharge rate, and that will be the Q bar figure. So this is the kind of thing that will happen when we're in clay soils. We'll typically be limited to the Q bar figure, and then the additional volume that we're generating will need to be managed on the surface. But these kind of targets have been around for some time, as I mentioned, and there's a range of additional criteria that we can look at as well when we're auditing. It's not just the hydraulics and the water quality per se. We need to look at the practical issues of pipe sizes, distances between manholes, depths of cover, and looking at all the economics as well as the technical nuances that were well covered with the Sewers for Adoption and Sewers for Scotland documents and the Greater Dublin Strategic Drainage Study in Ireland. And we have other documents globally as well that we're implementing, as well as Network Rail for the railway standards, for example, that have been improved recently. So we're going to run through a systematic auditing process, and I'd like to introduce you to Merlin the Wizard, who's going to help us with this. I just enjoy sharing this story with people because we have Ian Swatton here. Ian's the senior software developer for MicroDrainage and has been here since 1993. So with Ian reading Terry Pratchett's Colour of Magic book back in the late 90s, there was a character there called Rincewind, and it was whilst reading the book that Ian had this kind of image coming up in his mind that he thought, well, when we put wizards into the software, which we were developing at that stage, this is the image that came into Ian's mind, which he then generated as an icon that's now in the software. And we had a comment on LinkedIn from someone a month or so ago that said one of his favorite things about MicroDrainage was the wizards. And that triggered us off to research when he went into the software, which was in version 7, W7. And he was actually generated way back in December 99, early 2000. So 15 years young is Merlin, but he saves us a lot of time and effort. And he's a bit of a hero of many people, as indeed was Terry Pratchett, bless him. So we're going to use Merlin to audit an integrated model. And when I say integrated, looking at the image on the right-hand side, we have the flow conveyance system fully integrated with a range of potentially infiltration as well as attenuation structures and flow controls. So we will then take a look at what's happening post-development compared to the pre-development condition, and we can even go beyond that and identify the surface water flood routes. We can manage that surface water. We don't have to redesign the drainage. We just need to manage to make sure that we don't have this water entering into properties, protecting the communities for the long term. The start of the process, we need to understand the existing hydrology. So the site that we've been using pretty well consistently throughout the webinar series I've got shown here. The gross area of the site is about 7 hectares. The annual average rainfall is 900 millimeters in a year. The soil condition underneath, 0.15 soil index. So this is a relatively free draining site. So the runoff that would be generated, the standard percentage runoff from the site, from the Greenfield, is about 15%. And it's located in region number 2. I've just returned from a couple of days up in region number 2, actually, from Scotland, spending a couple of days looking at rail drainage design with folks up there. So interesting couple of days, and thanks for your hospitality there, guys. It was much appreciated. When we have that information, we can then calculate the peak Greenfield discharge rates that are currently occurring, and we identify for the regular return period, typically of a 1 year, 2 year, or 5 year return period, the 30-year return period, and the 100-year return period. And that all emanates from the Q bar figure, the mean annual flood figure. I can show you how to do that with MD sets, because I think a couple of webinars ago, we had launched MicroDrainage 2015, and we've released a brand new module called MD sets. So when we're looking at scoping out this conceptual work and designing some structures and linking them together, we can also look at the existing hydrology, deluge the site, and also identify the Greenfield discharge rates and the volume. So let me do that now with a live demo. Sorry for the long introduction, but I get mixed feedback. The vast majority of folks are saying they really enjoy the introduction and for me to put things into context. The odd folk will say, I'd rather you just showed me the software live and I want to learn more about it. If you need a lot more, don't forget we run training courses every month as well. So the idea is to show you what you can do. And then if you need extra help, then maybe you can come along and spend a day with us and we can run through these things in detail. We've got 6 different days of training right now. And I'm about to write a 7th one covering the MD SUDS module that I'm just introducing you to here, if you didn't see this with the launch in March. Looking at that particular site, here's the infrastructure layout generated by the architects that the poor old drainage engineers had to make work, in inverted commas. And what we've done is we've taken in the CAD drawing, which is showing you this highway and road drainage layout. I've also brought in the model of the highway that's been designed using a proprietary road modeling package. And then I've applied a deluge. So this has all been done through MD SUDS. So you can hit the deluge here, apply a depth of water, see where it's going to run to identify the blue-green corridors. And this is what I've been trying to emphasize folks doing before the architects get their hands on the land survey. I'd like you to deluge the land survey, tell them where the water is going to go, and then they can hopefully introduce the road layouts to satisfy the blue-green corridor and connectivity requirement to enable us to provide the multiple benefits. There we go. So what we can also do now is, having deluged this, take a look at the peak discharge rates. So I'm clicking on the rural runoff calculator. The most popular methodology is the IH124 report, Institute of Hydrology Report 124. If the site is less than 50 hectares, which this one is, it's 7, we use the pro rata approach. So we calculate the runoff as though it was from a 50 hectare site, and then we pro rata down to our 7 hectares. If I click on the ICP SUDS tab, that's exactly what the program will do for me. So I can put in the area of the site, the gross area, 7 hectares. I can pick from the map and identify where the site is. And when I've picked the site location, if I just move that around a little bit, you can see that you can pick the location of your development. It'll populate the annual average rainfall figure, the SAR, 900 millimeters in this case, and the soil type, 0.15. So immediately I'm thinking this is the more free draining of soils. And then the region. So again, you can pick on the regions. As I say, it's region number 2. Hit calculate, and then the highlighter blue row has identified for me the 1-year peak discharge rate, 3.3 liters per second, the 30-year 7.2, and the 100-year at 10 liters per second. It's also identified the Q bar figure. So the program uses the Q bar figure and then applies growth curves to generate the various return periods, and wherever you are, in whichever region, it will apply those particular growth curves for you. I've also put in an additional return period of 2 years if I need to set up a complex control. We could also calculate from here the Greenfield runoff volume, but I'm going to do this live in the software, in the MicroDrainage software, where the integrated model has been generated. So I'll show you how we can work with that within one of those Merlin wizards. So now, from MD SuDS, I'm now going to switch over into MicroDrainage. And the reason I'm doing that is because the engineers have designed a completely integrated system. We have a range of essentially pipes and manholes here in the model, but also a range of flow controls and also some structures. And I can take a look at this by clicking on the network drop-down. And if we come down to the online controls and see how we're controlling the discharges within and off-site. So there are a couple of controls, one further up the system, just to ensure that we're taking full use of the attenuation available in the upstream catchment. And then there's also a complex control. The complex control, when I see this, I'm thinking the engineer is wanting to hit these 3 different targets of the 1 year, the 30 year, and the 100-year return period. And we can see here, based on the depth of water within the flow control chamber, what the discharge rates will be. Okay, so that's giving you an indication that there's a relatively free draining soil. We're not in clay. We're looking at hitting those 3 figures. So we're feeling pretty confident that we're going to maybe end up with the same volume of runoff or less to enable us to be provided with the higher discharge rates, and rather than being restricted just to the Q bar figure. If I look at the network drop down, we can have a look at the nature of the structures that are within the model. And as per the Welsh Government surface water sort of storage ideas and incorporating pervious pavements or porous car parks, there are 4 porous car parks that have been introduced into the model. Looking at this one, structure number 1, on the right-hand side, we have the characteristics of that structure. So we can see the infiltration coefficient that's been used and the size of the structure, etc., all being taken into consideration here. So when the water level rises and the runoff is circulating through this porous car park, based on this footprint of 10 by 10, the flow will infiltrate out of the porous car park into the ground at a rate of 0.2 meters per hour. So as the water level rises in the porous car park, the program itself is calculating that flow going out of the system into the ground. At the bottom, we have a complex structure as well. So we had a complex control, and there is also a complex structure. That complex structure, if I click on the edit drop-down, comprises of an infiltration trench underneath an infiltration basin. Precisely the photograph that I showed you earlier on the left-hand side, with that infiltration trench running underneath an infiltration basin. So we can replicate those kind of structures within the program, and here are all the characteristics associated with it. And we can take a look at things in 3D. This is a 3-dimensional image of what I've just shown you on the plan view. If I just pick that up, we can see that there are a range of flow conveyance systems, mainly pipes and manholes. And then these little brown areas here, these are the 4 porous car parks further up the system. And then this is the infiltration basin with an infiltration trench underneath it. And we have a complex control at the downstream end to restrict the peak discharge rates off-site prior to connecting into a water course or a public sewer or whatever that may be. So let me introduce you to the wizards. And we could just carry out a hydraulic check using a seasonal return period wizard. We could also look at a range of climate change scenarios. So again, just a hydraulic check. For those working overseas outside of the UK, we can use the Rainfall Wizard with any rainfall that we have locally available. And that rainfall, that local rainfall, we can apply climate change scenarios to as well. If we have flooding at the end of this for the 30-year return period and we want to fix that in an efficient way, we can get CASDEF to fix any flooding issues if we wanted to. And if we're focusing specifically on those peak discharge rates and the volume, so code for sustainable homes type work, then you could use a Discharge wizard. I'm going to use the Design Audit wizard, which is essentially encapsulating everything above, plus I'm going to check things like distances between manholes, depths of cover, minimum pipe sizes, chamber ring sizes, all those elements that are covered in the other standards like Sewers for Scotland, GDSDS, and Sewers for Adoption type documents. So when I click on the wizard, Merlin takes us through a step-by-step process, and here we can tick on or tick off those elements that we'd like to check. So I want to make sure that we got the right size chamber rings applied to the pipe diameters and the depths of pipe used. I want to check the head loss, the manhole head loss. I'm looking over on the right-hand side, when the water is flowing down through a network, if it reaches a 90-degree change in direction, the manhole head loss in this, we're going to lose energy. So the manhole head loss should be increased in that particular manhole. At the end of this process, if any of the manhole head losses are too small, we simply hit an update button and the program will fix the manhole head losses that are too small and provide the correct ones based on changes in direction. This is assuming that you've carried out your design and we know the coordinates on the of the manholes and the changes in direction basically through the system. We can do a storage check, make sure there's no flooding for the 30-year return period. We can look at the minimum pipe diameters that have been used. In this particular case, I know that we do have 100mm diameter pipes. But when I was training with the guys on network or rail type schemes, I know that the minimum pipe diameter should be 225. So you can apply manhole pipes size files starting at a 225, and then we can check against a 225 option for those kind of rail projects. What's the maximum distance between manholes that we're prepared to accept? Check with the water company would be my advice. Some say 90, some say 100, some may say 150 meters. Depends on the kit that they've got. So typically 100 meters is okay, but generally not many would like it to be any further than that. But do correct me if I'm wrong. It's going to check the accuracy of the coordinates. The design has been carried out using a CAD drawing, so we're going to check the lengths of the pipes against the coordinates that have been calculated as well to make sure that the accuracy is 100%. It'll check for crossings and conflicts between a variety of different networks in the model if we wish, and we can check for minimum cover depths and maximum cover depths. We can look at the backdrop situation, whether they're little fiddly backdrops or whether we've got something that's a little bit too high coming in terms of health and safety. If there's anything higher than 1.5 meters within the chamber, then an operative may have to rod to clear a blockage overhead. So we don't want that. So we need to make sure that there's no backdrop deeper than 1.5 meters. And then we can put in our full bore velocity requirements of typically 1 meter per second, or there is no real maximum velocity, but you can start running a little bit quick with energy over 6 meters per second. But there's no requirement that I'm aware of in the standards to say that's a bad thing. I'm just really flagging things up. So we click on next. In your rainfall characteristics, we're going to check for both the summer and the winter profile events in one run. We're going to check all the different storm durations running from 15 minutes all the way up to 10,080 minutes. That's 7-day storm duration. Looking at something like 19 different simulations for summer, 19 different simulations for winter. So that's 38 different simulations Merlin's going to run for us. The 1 year return period, we're going to check for surcharging above the soffits of the pipes, which is acceptable because we're going to have flow controls within the system. So even with a 1 year return period, we'd expect there to be a little bit of surcharging. The question is, how much surcharging are we prepared to accept? And I'll say a meter above the soffit of the pipe would be fine in my mind. We're going to check for flooding for that 30-year return period. If you had a different requirement, we could change the return period here. These are just default settings that you can change. We're going to check for the proportional velocity. Now, this is one of my little criteria that I believe we've been missing a trick on over the years, because we design for full bore velocities, but of course the pipe network is typically not running at full bore for the vast majority of the time. It's only running at proportional depth. The question is, are the pipes going to silt up? What's the velocity when we're running at proportional depth across the network? This will help us to identify those pipes that will be more likely susceptible to silting up over time, to identify those areas at most risk right at the outset. And then we can put in any other additional return period, 200-year, 500-year, whatever. I'll leave it at 1. What about the minimum proportional velocity? Are we prepared to go down as low as 0.6 or 0.75? You can type in your requirements here. And what about the maximum proportional velocity, 6 meters or 7 meters per second? You can adjust this to suit your requirements or local standards. And now, this is the 5th step, where we're looking at putting in those Greenfield discharge rates. And those were calculated using the MD SuDS module. And I've put in the discharge rates here of 3.3 litres per second for the 1 year, 7.2 for the 30 year, and 10 litres per second for the 100 year. Now, the Greenfield rates were calculated as existing, so without climate change. However, we're now going to test post-development, including 30% for climate change on the 100-year figure. So this came through with the interim code of practice and the code for sustainable homes kind of requirements. And then in terms of the maximum allowable volume, the Greenfield runoff volume, we use the 100-year 6-hour event. This is shown in the bottom left of the screen here as the benchmark. This has come through from the interim code of practice, code for sustainable homes, and now the Welsh Government consultation document as the most common requirement. And we just hit calculate and add in the gross area of the site, the 7 hectares that I mentioned, the 900 millimeters of annual average rainfall, and then the standard percentage runoff of 15%, hit calculate, and there's our Greenfield runoff volume in accordance with the SuDS manual, which has actually been updated. So I do not believe that this will be changing, but there are other items within the revised SuDS manual that will come through maybe in July of this year for those that are implementing that within the UK. Say OK to this, and now our targets, our Greenfield peak discharge rates and volume targets are set. We can get the program to also test for this minimal discharge. What's the flow going to be for the first flush, that first 5 millimeters of rainfall that lands upon the impermeable surfaces? And then we click on next and finish. There's a heads up warning that we've got one pipe that's diving down pretty deep and steeply, but that's what it is. So I'm just saying OK to that. And I'm expecting the velocity to be very high as well in that particular location. So let's see what Merlin comes back with. It'll take a minute or so to run. As I mentioned, this is a 7 hectare site, around about 70 odd pipes, including those structures, and a development of 70 plus nearly 80 properties as the kind of density on this particular project. When the results come back, we have a summary, so we can see all the hydraulic calculations and a summary of all of those different elements as well to tell us whether we've passed or whether we've failed. This whole process, I've been advised by the engineers that we deal with on a regular basis, that minute or two that seems like an eternity when you're watching a webinar, I'm sure, but this would take you about a day of your time on this size of site to go through and run individual simulations and do a comparison to identify the critical storm durations for each of the aspects of the site. So here's the audit report. You can see that we've just run it live on the 29th of April, 12:37 in the afternoon, BST. We have 70 pipes in the network. The slope across the site is 1 in 41, so a fairly steep site. 1 in 41. Now, that helps us in terms of the sewers for adoption requirement. If the site is flatter than 1 in 100, we should be designing for the 1 year return period on the flow conveyance system. So this is telling me that the 1 in 1 year is the appropriate return period to be designing the flow conveyance. If it was flatter than 1 in 100, we'd use the 2 year. If there were areas susceptible to flooding already, or we had basements within the development, then we'd maybe go up to the 5 year return period. The programs use all these storms, and now we can see that we have some elements that have passed and some that have failed. Now, if I'm the guys in the water companies, I can just click on the pipe summary here, and then there's a complete breakdown of ticks or crosses. You can right click, and then we can send this back and email it back to the consultant or the developer to say, happy with all the ticks, but we need to do a little bit of work where pipe 5001, for example, has got an issue with cover. So just move that down. There's a little cross there. So there's a nice way of being able to provide the feedback. So if we look at that summary again, we need to interrogate things like the cover levels. It's just focusing in on the potential problem areas. Not to say it's failed and it's a bad thing. This is just a practical issue that we've got 7 areas where maybe we're either very shallow or very deep, one way or the other. We need to make sure we've got concrete surrounds on the pipes. If we need to be shallow there, that's not an issue. We need to just make sure that we've built in and engineered a solution. We've got full bore velocity and proportional velocities, crossings and conflicts, and the ICP audit. I'll just zoom in on the left-hand side and take a look at the cover level issues. So the program will identify precisely where the issue is taking place and for why. So the upstream cover level of pipe 5001, we're saying that we want the pipes to be between 1.2 and 6 meters deep max, so at least 1.2 deep. Otherwise, if it's shallower, we need a concrete surround, or no deeper than 6. We're kind of getting into tunneling territory or micro tunneling if we go over 6. And this is telling us what the situation is on a pipe by pipe basis where we're outside of that range. So there's pipe 5001 is at 900 mil depth of cover to the soffit from the ground level. That may be in public open space. It may just be that it needs to be shallow for whatever reason. So it's identified the issue. Again, we can right click and this information can be exported. You can save it out to Excel or HTML around your colleagues and say, could you have a look at this and fix it? Or maybe just give an explanation as to why it is that way. The full bore velocities were also being flagged up. So we got a couple of them that are just a smidge under the 1 meter per second self-cleansing velocity range. So we need to just increase the gradient a little bit to meet those. S1016, that's the pipe that's shooting down steep that I was expecting to fail because of a maximum velocity. Is running a little bit quick at the 7.46 meters per second. Some of the local authorities in Wales will say that they'd like that to be less than 6. That's the only thing that I'm aware of. But again, please let me know if you know of any others that are flagging that up. We don't automatically fix that in the software. We just identify the issue so that the engineers can fix it. Proportional velocity, where we see the zeros, there's no contributing areas basically. So I'm not too concerned about that. But there are a couple of spots where we're running very, very slow, less than 0.3. So I know the grits are going to start dropping out in that particular pipe there at 0.26 meters per second. So we need to take a look at some of these issues and fix them. Crossings and the conflicts, we've got a couple of elements where there's a horizontal separation of only 421 mil between pipes. So you may have to have a look at that pinch point and put in some sort of concrete protection, maybe. And finally, the ICP audit. I'm kind of skipping through the others a little bit quickly on the engineering side just to get down to the ICP audit, which is the sort of the main push that's coming through from the Environment Agency and the local authorities and those code assessors for the Code for Sustainable Homes. So we can see there are a couple of tables here. The first one is identifying what the Greenfield discharge rate is for the 1, 30 and 100 year return period, and what the post-development discharge rate now is. So we are just a smidge under at 3 post-development compared to 3.3 pre-development, bob on with the 30 year at 7.2, and then we're just a smidge under at 9.8 versus 10 target. So the peak discharge rates post-development are satisfying the criteria. If I move down to the next spreadsheet, this is the volumetric runoff. So the Greenfield runoff volume is 797 cubic meters. We're now actually discharging 192 cubic meters. So the poorest car parking areas and the infiltration trench and the infiltration basin basically are doing their job for us. We're infiltrating into the ground where we can. We've reduced the volume of discharge, but we've reduced the volume that the developer has to provide under the ground as well. So we're saving the money by utilizing the ability to infiltrate into the ground. So it's a win-win. And at the end, the failure in terms of the ICP SEDS is the fact that we do actually have some discharge for the first 5 millimeters, and that discharge is 2.1 liters per second. So if we needed to put in some extra pollution removal or oil interceptor tanks or something like that, that's the flow that we need to address, 2.1 liters per second to set that up. We can take a look at a summary of the hydraulics, and we can use the storm selector here and get Merlin to sort out and sift through all of these simulations for the 1 year, for the 30 year, for the 100 year summer winter profiles. We've got over 100 simulations that was run in that minute or two of the audit. And if I click on the top here, you can see 2 little warning triangles. If I click on the right-hand triangle, critical by return period, if we look at the return period in the window, in the storm selector window, it's the 1 year. So the program has now run through and looked at the highest water level being met in each of the manholes, in each of the locations throughout the network. And it's telling us which storm duration is critical in each location. So generally it's the 15-minute winter profile, 1 year event. But when we look at areas where there are different structures, it may be increased to say 30 minutes or even up to 120 minutes when we get to the downstream end of the network. And this is showing us our maximum discharge rate at 3 liters per second, below the 3.3 target that we have. If I use the storm selector and just choose any of the 30-year return periods, it's doing the same job. And what I can do here now is use the flags on the top toolbar here, and I can switch off the blue flags, which is switching off any pipes that are still flowing within the pipe, where the flow is flowing within the pipe. I can switch off those surcharge pipes. And if I switch off flood risk, I'm just left with those pipes that are flooding. And we cannot have any flooding for the 30-year return period. So this is telling me that the system is actually performing in accordance with the standard. We don't have any flooding for the 30-year return period. And we've run all the storm durations from 15 minutes up to 7 days with the different profiles. We do have some flood risk in areas. I'd expect that where we have car parking areas specifically, because the car parks are literally on the surface, as per the Welsh Government document. And then let's take a look at the 100-year return period, and I'll switch off the flood risk. So 100-year return period plus 30% for climate change. And I would expect flooding. This is the whole purpose of the exercise, is to create the flooding. And then what we can do is we can run analyses and identify the overland flood flow routes post-development, and make sure that the depth of water is no deeper than, say, 150 mil alongside the properties, so that we don't have any internal flooding, again, as identified by the Welsh Government consultation document. So we've got some flooding, and you can see the flooded volumes. We can run exceedance tests on that in a future webinar. But this has, in minutes, run through and saved us a day's worth of grief, basically. So looking at the conclusions now, if I just move on to wrapping up the webinar, just looking up at the clock and seeing how quickly the time goes from my side. I hope you've enjoyed that and appreciated the speed that we can provide you in terms of productivity savings. So for every job of that kind of size, I'm being told that you're saving about a day's work in terms of going through that analysis. This will also enable you to gain swifter approvals. We can extract reports from the program to show you how you've run all of the different scenarios, and we can export those summary of results and provide that as evidence to the approving bodies. So looking ahead, just to advertise a few events that are happening this month. It's a really busy month, which is great. 13th of May, so where are we now? About 2 weeks away. We have an ICE flooding event in London. This is central London. We're platinum sponsors along with others like Hydro International. So Ludmila Fadeva and myself, at least will be there. I'll be speaking at the conference, and we will be running a workshop in the lunch hour along with the other platinum sponsor there, Hydro International. So looking forward to that. We did a similar thing last year. It was literally the same day, actually. I think it's 13th of May, but 2014, and really well attended, a great occasion to come along to. And it's being held at the Royal Garden Hotel this year in London, so fairly central. Hope you can make it. If you do, pop along and say hi to Ludi and I, and we look forward to you participating in the workshop and seeing you at the conference. The other things that are happening, we've got some training. So the auditing aspects that I've run through today, this is all contained within a one-day training course, which is Training Course H. We're actually running that here in Newbury on the 21st of May. So if you really want to get your teeth into the software and go through all of this process and build up your confidence and competence with the software, then feel free to apply to come along to the training. We're running 4 days of training from the 18th to the 21st. At the end of the month, a couple of things happening there. 27th and the 28th of May, colleagues like Jenny Granger, Tom, we're going to have Carla over in Montpellier in France at the Hydrogia conference, which is a 2-day conference. Not sure if anyone's tuned in from France here today, but if you are, then be great if you pop in and see Jenny and Carla and Tom. And the next webinar, thanks for your feedback. I really do value your feedback. I'm really pleased to announce that Joe Bradley from the Environment Agency will be our first guest speaker, and the webinar will be held on Wednesday, the 27th of May. It'll be at the same time. It's going to be at midday. And what Joe's going to do is run through the water quality aspects from the approving authorities perspective, from the Environment Agency perspective. So what we're looking at are the risks associated with water quality that the Environment Agency are now producing pollution prevention and control solutions for, and how those SuDS elements can provide opportunities to help to address those issues. And we're thinking of things like the EU Water Framework Directive. Joe's been with the Environment Agency for 23 years, so she's got a lot of experience, specifically on the water quality aspects. She's the Highway Outfall Project Manager for the EA, and I'm really looking forward to Joe's participation on that. She's been involved with a number of working groups. She's very active and involved with the rewriting of the SuDS manual, etc. So delighted to have Joe along, and I hope you'll be able to join us. We'll send out the link, and you can register in the normal way, and that will be for Wednesday, the 27th of May. And until then, I hope you all keep really well. Thank you very much for your participation. I look forward to joining you all again, either at the conference or meeting you somewhere, and if not, at the webinar at the end of May. Take care for now. Bye.